Okay, we're still on the topic of feature engineering. However, we're going to start doing a different type of feature engineering. With these three pills, we were converting data into different forms, whether mathematically through these two or simply changing the data type with edit metadata. What I want to do now, first of all, give us some room to work here. I'm going to delete a few of these. What I want to do now is learn a different type of feature engineering where we're going to what's the word I'm looking for? We're going to increase the coarseness of the data, simplify the data, or reduce the granularity of data. Let me give you some examples here. So I'm going to delete these, and let's take a look at our lending club data one more time here. So there's one field that I've learned is fairly useful in this data set to predict loan status. It is the purpose of the loan, right here, purpose. Okay, so we have this histogram representing in order which purposes are most common. We've got, I don't know which one's this top one, but we've got, I think, 13 total purposes. Are we getting a loan for medical reasons, debt consolidation? I think this is pay off credit cards, and I don't know how different that is from debt consolidation anyway, but to buy a car, home improvement, house, it's probably an initial house payment, which technically you're not allowed to do, but whatever. Wedding. Let's say these 13, it's too many categories. I want to reduce them down to something like credit card and debt. That's really the same thing in my mind. All right, so I've got some tools to allow me to use that, to do something like that. Let's first start with the group categorical values pill. So group. Actually, we're going to go through and learn each of these. No, I'll just start with this one. Group categorical values. Okay. Let's pull this out. And very simply, I want to say, all right, let's grab that field, purpose, and output mode. We learned this from the prior video. I always want to do append at this phase because I'm not in the modeling phase yet. I don't know if my new simplified version of purpose is going to be better or worse when it comes to predicting. Sometimes when we have too much detail, it's actually worse for certain algorithms because there's not a good shape or spread to all the different possible categories I have, and it makes more sense. And a lot of the categories are very highly similar, and some algorithms don't like that. They want independent variables, not very similar variables. They want different ones. So I don't know if it's going to be better or worse yet. So I always want to, at this point, append. I don't want to do in place because then it will replace my existing purpose variable. So append means give me a new one. So default level name. This is something we only need if there are some values that we don't really know what to do with, or we aren't sure. Let's say we have, we're trying to take the field, let's say we're doing something different like the field loan title. And most of the titles have something to do with, or here we go, employment title. We see like here 2 different post office titles. Let's say for some reason most of our data was post office and 3 other things and then a tiny few others. What I could do is I could have a default name for anything that I don't explicitly map to a new title. And anything that's not mapped is going to go to the default name like unknown or something like that, or other. So for now I'll put in an other, but I don't really intend to use this. Number of levels. So what do I want to go to? Now there are 13 original levels in that data set. I noticed because I'm familiar with it. Let's take it down to, I want to make it really simple just for example's sake, 3. So name of new level 1, let's call this debt. And that's going to include anything. So it says comma separated list of old levels mapped to new level 1. So we had one called debt consolidation and credit, was it capital C? I can't remember. And honestly, I'm not sure if it's case sensitive or not. I've forgotten. We'll find out here as we go. Let's take a look at those values again real fast. It was purpose right here. Oh, debt underscore consolidation, credit underscore card. Okay, cool. Make sure I get that right. Debt underscore consolidation, credit underscore card. Okay. Level 2, I'll say this was something to do with home stuff. And I remember there was one called house. And there's also one called, oh gosh, now I can't remember. Sorry. Something to do like renovating or remodeling. Oh, here we go. Home improvement. Where was it? Home improvement. Just copy it. Okay. Home improvement. Okay. And I changed my mind from 3 down to 2 because I want to keep this simple and get moving. Oh gosh, it resets all of them? Of course it does. Yeah, seriously. Oh no, 3 included my other category. Okay, good, it's all still there. So I've got category 1, debt, category 2, home, and anything that's not one of those 4 is now going to show up under other. In reality, this is not likely what I would want to do for this particular data set, but I just want to illustrate the point and show you how this column works, or how this pill works. So let's let that run. Okay, I got an error, and I wanted to leave this in the video because I think it'll be useful for you to see, because you'll probably run into this error at some point as well. So it says, column with name purpose is not an allowed category. Remember how I said we sometimes use edit metadata to specify very clearly what type of data we're working with. A pill like group categorical values, it's very specifically intended for categorical fields. Sometimes we have to use edit metadata because, again, purpose came out of the database. There's more than one type of string or text field. There's many different types. So sometimes we just need to explicitly cast or transform a field into a certain type. What we want to do is say, let's take that lone purpose field and let's make it categorical. Even though you think, well, duh, it already is. Sometimes, again, there's this metadata that we need to be a bit more explicit in changing it to what we want. So purpose is right there. Check. We're going to make it categorical. Don't need a new column name. We're just going to let this one run, and then it should be fine making our transformation to group categorical values. So I'll leave this running just to see if I run into any more errors, if this works out okay. Thinking. All right, maybe I need to pause. That was a bad idea. All right, I don't know about you, but my edit metadata took forever. But the second that finished, it worked out just fine. So let's take a look here at group categorical values. Visualize. Okay, let's scroll over. And it should be, I think at the very end, yeah, purpose 2, it called it. I didn't give it a new name. So it's either other, debt, and that counted for either debt consolidation or credit card, or home for home improvement or house, and everything else was then other. Which really, yeah, debt is most of it, isn't it? Anyway, so I would keep both of these and then find out if this one versus the original purpose, which is still, of course, right back here, does a better job of predicting loan or whatever the dependent variable is during the modeling phase. So that's group categorical values. Let's leave this since we've learned it, and let's use something else now. All right, and let's use this group data into bins now. So group categorical values was for reducing or simplifying the complexity of categorical values. Group data into bins is for reducing the complexity of numeric values. So let's actually start by using the annual income field as an example. So I've already gone through here and selected it. Grab annual income, move it over here into selected columns. And there's a bunch of different ways to bin. And I think rather than go through all of these, I'm going to show you some of the more common ones. And let's go straight to the documentation because I think that's an easier way to understand it. So let's go group data into bins and take a look at binning mode. So here's some examples. Oh, I love this. Here's the raw data. Most of the values are here in this -52 to 3 range, and fewer values as we go up. Using the quantiles method, this is a way of saying, all right, let's take that data and spread it out more by dividing it up into different spots. Now they normalize the data first, like we've done before. First they normalize the scale, and then they say, okay, about 1/10 of the cases fit here in this range from here to here. And they choose these cutoffs to make these bins as equal as possible. So that's what's happening with the quantiles method, which is this one that's selected by default. And it normalizes how do we normalize? It turns everything into a percent of the maximum and minimum value. Here's the variable, and let's go ahead and run that. I've run it on mine already, so I'm going to go ahead and view. So pause this if you need to while you run yours. So here's our standardized scale. First of all, this is a percent here. It's standardized it, and it's given this first one a value of a bin that if it's in the 36% bin. That's like the which bar is it represented in which range. So it's the cutoff of that bin. So now I have a much more normally distributed annual income variable. Well, actually, no, sorry, I take it. It's not normally distributed. It's evenly distributed. Let's go through some other possible methods. So that's quantiles. Let's show you some other options here. Binning mode, equal width. Okay, so this is the first one we looked at. Quantile method assigns values to bins based on percentile ranks. Equal width. With this option, you must specify the total number of bins. The values from the data are placed in the bins such that each bin has the same interval between the starting and end values. So this is like the, let's turn income into, are you in the 0 to 10,000, 10,000 to 20,000, 20,000 to 30,000 range. So you may have some reasons for that, but that's the one that I was trying to get away from with income, but there could be reasons to choose that. You can also choose custom edges. This one is something I do a lot, and I'll show you how I use it and why. To do that, I actually want to go back to the bike buyers data and remind you of something that we did before. All right, one moment here. Let me pull that data in. So I think it's easier to understand this concept if you can visualize it. So let me pull it in. I'm going to use Excel for now, just because I don't have the ability. I don't use Azure for making visualizations as much, although I can. Excuse me, this will be a bit quicker. So I want to show you the relationship between age and purchase bike numeric. Oh, do I have it? Yeah, here's the numeric version. Perfect. Let's insert on that a scatter plot. And let's insert on that a trend line. And let's view Trendline Properties. Format trend line. And I want to put on there the r squared and the equation on the chart. So this is the y equals mx plus b equation. All right, we went over this a little bit in the statistics chapter, the previous chapter. So hopefully you remember some of this. What we've got here is a line that slopes downwards, which means that as people get older, they purchase fewer bikes. So if I look at that and I see an r squared of 1%, which means it's not a very, this single line doesn't do a great job of explaining whether the dots are up here or down there. If I just assume, okay, that's as good as it's going to get, I would leave age as it is and make no transformations. But come over here to the Trendline Properties, I click on that, and I click on logarithmic, and I see, okay, r squared gets worse. What about polynomial? Actually, it gets much better with polynomial. R squared is doubled from what the original straight line was. It's 2% instead of 1%. All right, that means that actually right here, from where our age begins, the likelihood of purchasing a bike actually goes up until they hit age 40. Then it appears to start to go down, and then it really starts to go down fast. Interesting. So what this tells me, actually, let's go up to a third order polynomial and see if that improves anymore. Okay, now I'm up to 3%. 2% to 3%. How about up again? Okay, if I go to 4, it doesn't really improve much. My r squared only goes up to 3.33. So I would say that the best trend line that fits the data is a third order polynomial. And that says that people get more likely to purchase bikes until age 40. Then they've had all the kids they're going to have. Their kids have bikes. They start slowing down as they get older and purchasing fewer bikes until about age 75. Then their grandkids start needing bikes, and so they start buying their grandkids' bikes. Okay, that's useful. It's two different types of bike buyers. And depending on their age, their likelihood's actually going in different directions. It's going up here, down here, back up here. I really need to mark age 40 as a breakpoint and age 75 as a breakpoint. So I want to break my age into custom bins. And maybe all I'm going to do is say, are you 20 to 40? 40 to 60? That's where there's an inflection here, where the rate of decrease is increasing until about 60, and then the rate of decrease decreases until about 75. So I'm going to go, and I'm just visual. This again, this is the advantage of visualizing data. I'm going to say break the bins from 20 to 40, 40 to 60, 60 to 75, and then 75 plus. That's a better way to bin age so that it explains my dependent variable. Perfect. All right. Hopefully that made sense. I'm going to come back here now, and I'm simply going to say custom edges and comma separated list of bin edges. Now, if this was age, what I would do here is I'd say, okay, my first was 40. Actually, it kind of looked like it might be 39. Then I go to 60. Then I go to 75. And then that's it. So it would group people actually into 5 bins. Up to 39. No, sorry, 4. Is that what I wanted? I've forgotten. 1, 2, 3, 4. Yeah, 4 bins total. Up to 39, up to 60, up to 75, over 75. But I'm dealing with annual income. I'm just going to arbitrarily pick some numbers. Let's say 20, 30, 1,000, 40, 2,000, 51. I just want to show you how this actually works here. Append mode, great, run. So what I would do is group data into bins using a variety of methods that you think might be useful. But how do you choose? I mean, there's so many different options. That's where doing the data understanding phase properly is so critical. It took the visualization. Now we did it in Tableau. I just did it in Excel here because it was quick and easy. But doing my visualizations so that they inform the data preparation phase is a great way to streamline your work and make sure that you're not just throwing a net around every possible option out there. It helps you focus in on what's really going to do some good or help my prediction later on. So do your data understanding phase right so that when you get here, you know exactly what it is that you're doing when it comes time to engineer your features. All right, let's see what this looks like. Oops, visualize. Scroll down. All right, so this tells us now which bin they're in. Are they in the first bin, second, third, or fourth? And that's it. Something I could do, one more thing I would do right here, just so you know. This is important. I don't want to lose this. Since we found that the effect from here to here was different from here to here and there to there, what I would do next is change that numeric bin assignment to categorical. So I would actually edit this metadata and say now, because the bin that they're in could have either a positive or negative effect on the outcome variable, I would come here and I would make that variable that was created in the prior step, annual income quantitized. Get rid of this one. I'd call that a categorical variable so that it treats it as independent categorical age groups and it doesn't order them. It doesn't say that age 2, the bin number 2 has a stronger effect than bin number 1. Bin number 3 a stronger effect than 2 and 4 greater than 3. See, if I leave them as numbers, it implies that a higher numbered bin has a stronger effect on whatever the dependent variable is than a lower number bin. But that's not the way it is. This effect actually reverses entirely. So I don't want it to treat bin 2 as having a more positive effect on the dependent variable than bin number 1 because it actually reverses. So what I do is I make it categorical and have it treat it as different categories rather than numbers entirely. All right. Hopefully that's made sense. If not, let's talk about it in class. We've got one more pill to show. So this is what we call principal component analysis. This one is another fairly complicated one that we'll probably want to practice in class together, but let's show it here in this video. What PCA does, it's another way of simplifying and aggregating your data to a higher level, and it's extremely useful. So let me find you a good diagram of what PCA. All right, perfect. So In this video, I won't have time to explain it in detail, but I'll give you a link to a good YouTube video that will. Here's what PCA does. It says, all right, we've got data. Let's see if this will get to a higher quality one. Okay, perfect. So I've got data that I can plot along a few dimensions here. And I've got 2 dimensions. And the data doesn't follow a very standard direction anywhere. In fact, it's kind of going out all over the place. What a PCA does is it says, let's start drawing lines through groups of data that are chunked or grouped together. So I've got multiple variables, and I've got, let's find another one here. All right, I've got one, in this chart, I've got some data that appears to go this direction, but also notice around the middle of this data, it starts to fan out a little bit more in the middle, this direction. So I've got there we go, one component going this way and one component going that way. So let's take these variables and redefine them in terms of their place along this component and their place along that component. Now this is only 2 dimensions. You can plot 3 dimensions and have more components. I can plot every dimension is another variable. In my bike buyers data set, or my London Club data set, I have like 50 variables. I can plot 50 dimensions, and then I can start drawing components through the clusters or chunks of data that appear most common. So it's kind of like taking that ability to draw a trend line in Excel or Tableau and saying, well, we can draw multiple trend lines coming from multiple directions to represent where this data is truly going. Let's see if we can find another example. Here they've said, okay, yeah, we've got 2 variables, and really we've got one dimension going this way, one trend line going that way, one trend line going this way. Let's see if there's a good 3-dimensional example. Here we go. Now I've got 3 variables, 1, 2, 3. Out of this, I have one that's kind of going this way through all 3, one that's going this way through all 3, and one going that way through all 3. So the principal components analysis says, let's take the variables, plot the data across all variables, and let's draw trend lines, as many as needed, to fit the direction and flow of the data well. So it's kind of like relaxing the trend line assumption to allow for multiple trend lines in a chart. So the advantage of that is if I do have 50 variables, I can reduce those variables down to a smaller set of relevant trend lines. So let's give you an example. Back here, I'm going to move this over. Let's do a PCA by taking all variables we want to use to predict whether or not they're going to pay off a loan. I'm going to grab, there's a bunch of these ones from their credit report that are very similar, that it doesn't really help me to have their total revolving high limit as well as their total current balance as well. You know, some of these are very similar. So what I'm going to do is grab all of them up to DTI. These are all my credit score variables. And I want to plot a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18-dimensional scatter plot. Now we're not going to see this. It's going to do it in memory. Plot an 18-dimensional scatter plot, and then draw a few trend lines through that scatter plot. How many should I draw? I can tell it right here. 1, no, clearly more than that. How about, and there's some guessing involved here. So let's start with 4 trend lines. Okay, so let's draw 4 trend lines through those variables and see what it comes up with. And what it'll do is it'll give us a score across each of those trend lines for each record. So let me pause this. Let me see. Okay, so let's right click, result data set, visualize. So what it's going to do, it's going to add or append to the end here 4 new columns. And it says, okay, this is trend line 1, 2, 3, and 4. And so for each one of these record sets, it took all of those other variables that we included, and now it's removed them. It turned those into their score along 4 trend lines that are meant to be as orthogonal as possible. Notice back here, the trend lines that it draws, we try to make the direction of these trend lines as different as possible. Another word for that is orthogonal. Because when we model later on, we want our independent variables to be as different from each other as possible. For example, if I'm going to predict who's going to buy my bike, I don't want to include both their age and their birth date. That's basically the same thing, right? They're too closely related. It doesn't do me any good to measure both of those. Or I don't want to include education and income, because maybe there's a really strong relationship. As people get more education, they get more income. Now, maybe that's a bad example. Maybe they're not that strongly related. But the idea is I get these variables that are very similar to each other. I don't want to eliminate one. I want to use both of them, but I want to reduce them down to a set of trend lines plotted through all those variables that capture the variance going on. So PCA took all of those, how many variables I had back here? It was like 18 or something. And it turned it into a smaller set of orthogonal or different variables, which we simply call column 1 through 4. Now, which variables are going into each of these? Well, think back to the trend line here. This line is representing, so this dot right here is plotted. It's got a value on variable 2 and a value from variable 1. This trend line is representing both of those variables to a certain degree. So it's not like one variable goes into one trend line and another variable goes into a different trend line. Rather, each variable plays some role in both of these two trend lines. So one thing Azure doesn't do a good job of is letting you understand the results of the PCA. In fact, I have no option at all to see which variables went into which ones of the components. There are other tools that will do that though, but PCA won't. So for now, we'll cover PCA again later on. Just know that we use this to take a larger number of variables and reduce it down to a smaller set of orthogonal or independent variables. Whew, that's a lot for one video. Simplify categories, simplify numbers, simplify a bunch of variables down into a smaller number of variables. That's this type of data preparation. What I would do in practice, again, I would probably, with PCA, before the way I would choose which variables are going to go into it, I would look at, for example, all the variables that I'm including in the PCA and try to use my business knowledge or my theory to say, okay, how many different dimensions are truly being represented? In a credit report, there's how long you've had credit, how much you owe, and how many bad things are showing up on your credit. Maybe those are my 3 dimensions I think are being represented across all of these variables. So I would use my theory to say, okay, really, truly, there's only 3 dimensions, or however many dimensions represented by those 10, 15, 20 variables, and that's the number I would choose here to come up with my PCA. Now, in practice, what will happen is we'll run a PCA, choose a number, send it to the modeling phase with those variables. They'll come back and say, all right, it didn't do a good job of predicting whether or not they paid off a loan. So we'd come back and say, all right, let's try another PCA and let's go up to 6. And we send them back data analysis with 6 trendline components or 6 new columns. And then they say, oh, this was better. Okay. And then we might come back and try 1 or 2 more. We might try, all right, 6 was better. Let's go up to 8. And they say, no, 8 wasn't good. That was worse. So we say, okay, let's go back down to 6. And we just keep trying until we get the best possible prediction from the modeling phase. But from now, we're not modeling it yet. I would just say, pick a number, run the PCA based on your theory or your domain knowledge of those variables. Okay, that's it for the feature engineering phase of data preparation.